Welcome back, guys. In this video, we're gonna generate the equation for the work of a spring force or of the elastic force. Previously, in the previous video, what we did is to find the equation of the work for the weight. The weight is very different from the spring force because, in fact, the weight is a constant vector. It's constant in magnitude and it's constant in direction. So we can remove this weight from the integration of the equation of the work, and then we can find out the work of the weight, since the weight is independent of the position. Oppositely, guys, for the spring force, I know what is the equation of the spring force. I know that the equation of the spring force, Fs, is equal to what? Fs is always equal in scalar value to minus k times s. What is k? K is the constant of the spring, Newton meter. And what is s? S is the position. So k, guys, is a constant while s is the position. Now, this means, guys, that the force inside the spring or the elastic force is not independent of position. It's depending on the position. If I want to do the differential equation of the work for the spring force, it is in fact minus ks ds. Why? Because I know always, guys, that the force of the spring is in a collinear to the displacement. So I'm going to do this. dus is equal to minus ks ds. Now, if I want to do the integration, this means, guys, that us is equal to minus the integration of ks ds. Which is what? I can remove k from the integration since this is a constant. It is a constant that depends on the type of spring. It has the unit of Newton per meter. Alright? So what is the integration of s ds between, of course, the position? It's in fact s squared over 2. Alright? So the work of the elastic force is minus k s squared over 2 between S1 and S2. Now, guys, most of the students forgot this over 2. Why? Because in fact, what they do is to make the product between the force and the displacement without doing the integration, which is not correct. Because in fact, this force depends on s. So I should do the integration to find the work of this force, alright? So if you do directly the product, which is not correct, you're gonna have this one, this equation, ks times s, which is ks squared. And this is totally wrong, guys. So this is total, of course, I forgot the minus sign, and this is totally wrong. This is not correct at all, alright? So the work of the spring force is minus k s squared over 2, which is what? It is half k s1 squared minus s2 squared, because I remove this minus sign, alright? And I multiply s2 squared minus s1 squared by this minus sign, so I'm gonna have this equation, alright? So the work of the spring force between position 1 and 2 is equal to half k s1 squared minus s2 squared. I want you guys to remember from kinetics. What is s1? Remember, guys, because most of the students also had a wrong answer for s1 and s2. What is s1? s1 is the current position at t1. Now, what is s2? s2 is the current position at t2. All right. Now, if I want to find the equation of S1, S1 is L1 minus L0. What is L0? L0 is the initial length where there is no forces on the spring. S2 is not, guys, L1, it is not L2 minus L1, never. It is L2 minus L0 also, guys. So it's always minus L0, which is the initial length where there is no forces exerted on the spring. Alright? So always, guys, S is equal to L current, the length of the current length of the spring, minus the initial length of the spring when there is no forces. Thank you.